Good afternoon, everyone. Myself, Professor Desai, Assistant Professor in Mechanical Engineering Department of RNG Patel Institute of Technology, welcomes you all in this wonderful knowledge sharing webinar series. Today, we are with us Dr. K.B. Rathore, Head of the Department Mechanical Engineering. We are having our expert, Mr. Anil Patel, a researcher from the Germany. And we are having our the moderator, Professor Sapan Joshi, Assistant Professor in Mechanical Engineering Department. Now, I request Dr. K.B. Rathore, sir, to introduce our today's webinar expert. Over to you, sir.
Thank you, Chirag. Good afternoon to all once again. Myself, Dr. K.B. Rathore, Head of Mechanical Engineering Department from Patel Institute of Technology, Bardoli, welcomes you all on the 32nd webinar of the Mechanical Engineering Department and 164th webinar of the college under SSIP cell. The topic of today's webinar is safety engineering in autonomous vehicle. And to deliver such an important technical topic, we have with us Mr. Anil R. Patel, who is a researcher from German University. And to more about him, I request Professor Sapan Joshi to give brief introductions about Mr. Anil Patel. Over to you, Sapan Joshi.
Thank you, sir. Hello, good afternoon all. Myself, Sapan Joshi from Mechanical Engineering Department, RNGPIT. Mr. Anil Ranjitbhai Patel is a researcher at Department of Software Engineering Dependability at Technical University of Kaiserslautern since 2019. He works on the virtual engineering of smart abandon system and dynamic risk assessment techniques. He has completed MSc in Commercial Vehicle Technology from Technical University of Kaiserslautern, Germany. He also maintained an active interest in safe autonomy related to autonomous system, collective intelligence of smart abandon system, and dynamic safety management in resilience achievements architecture. He was born in Surat and completed his diploma and graduation from Surat GTU. Mr. Anil Patel has also worked as lecturer in Government Polytechnic Bharuch. He further he has studies in Germany. Now over to you, Mr. Anil Patel.
Thank you, Mr. Joshi sir, Mr. HOD sir, and Chirag Desai for your kind words and introduction. Hello, everyone. As you all know, that I am Anil Patel. Today, I'm going to deliver a webinar on safety engineering in autonomous vehicle. Before start, let's have one question: that did you know that why safety is important for autonomous vehicle, or have you heard about autonomous systems and their capabilities? Well, today I will share my knowledge with you on safety engineering autonomous vehicle. But before I start, let's have a look what I have to offer today. So I will first talk about my department, which is Software Engineering Dependability Department at the UK. Then I will talk about autonomous vehicle. I will also share some of my knowledge on safety engineering. What I also want to share with you my present work in this domain of autonomous vehicle. And Chirag sir insisted me to explain about life in Germany after bachelor's degree for all students in RNGPIT. So I will also share my experience with you all. So we are safety and software engineering and dependability department. Our professor Ligesmeyer is the head of department. He is also director of Fraunhofer Institute for Experimental Software, which is basically a research institute for experimental innovation in direction of embedded system. And we also focus on dependability, safety, security, reliability, and availability characteristic of embedded system, as well as we also are looking for a new approach in dynamic risk assessment, as well as safety assurance under uncertainty for autonomous systems. Currently, we have two projects ongoing, which is collaborative embedded system and virtual engineering of smart embedded systems. And my part is dynamic safety management in resilient architecture, which I'm working on right now. You can also look for some of the information about this research on this link. So let's start with our topic, which is safety engineering in autonomous vehicle. But before that, we have to find out what is system and technical system. So in system, we call it technical and organizational means for the autonomous fulfillment of a task. Okay, in that we can say that whatever hardware, software, people and maintenance, personal and logistic assistance is considered, it's called a system. So take a railway station or airport where you have an airplane, you have a air traffic controller, then you have ground personnel for guiding the plane, then you have fuel supply systems, and you have ticketing. All this called a system. How it differs from the technical system, it's called where you don't have any influences by people and logistics. So you ignored people and logistics, and you only have a system which is called plane, bus, car, which we can call it technical system. So this technical system is basically consist of kind of function which fulfills their requirements. So a car is composed of a subsystems that call engine, steering systems, and brake systems. And each of these systems, let's say the engine system is also consist of multiple subsystems for fuel injection, for ignition systems, and so on. So this hierarchy of technical systems spans from the least complex, which we can call smartwatch in your hand, to and most complex from rocket propulsion system. So this kind of technical system we are today evaluating, and we see how it can be evaluated. So present technical system has many microprocessors installed in that, and those are varies from the safety not safety critical to safety critical. Not safety critical, we can say, is your cellular phone, which also has a microprocessor and sensors, but it is not safety critical. Even if your mobile won't work, it don't hurts you. However, other safety critical systems are aircrafts, trains, cars, and medical equipments. Aircrafts, if 8,000 altitude, your engine won't work. It's a safety critical. The lives are in danger. That's why we have to take into account all safety critical systems into safety engineering. And for that, we are evaluating safety, reliability, and availability for that. But today we are focusing only on cars. So let's take how the paradigm change in the automotive business. So let's take a model from 1949. It has a 40 cable connection and 60 switches. Over the period of year, now we have 1919 S-Class. There are 3 bus systems, 60 ECUs, and 110 electric motor. But in present car, if you call it, it has a cumulative length of electric wires in modern car is more than 4 kilometers compared to few hundred meters 30 years ago. And in modern cars, up to 150 ECUs are used, in commercial up to 40. So what I mean here is there are dramatically changed from the mechanical components to electrical components, and those components are vulnerable for some of the environment changes, and those things we are evaluating today. But before that, I want to share with you one simple video where why we have to evaluate this safety engineering, that we can see from this video. You can see the autonomous driving vehicle is colliding with the pedestrian running with her bicycle. From the interior view, the driver is busy with his mobile phone. Maybe he is chatting with someone, and then he has no attention at all on the road. And suddenly when he realized that something happened, time is gone. So the point is, what's happening in this is this car, which is collide with the pedestrian and the vehicle, it has 3 main components. One LiDAR is on the top, forward camera array on a rear view mirror side, and the radar on the front. So this 3 component has predicted completely with the street lights and surrounding environment, vegetation, and all those things. Even it also detected a vehicle in here. However, The dark condition of this environment, the vehicle didn't predict it. And when vehicle saw the bicycle with the pedestrian, it didn't realize that the reaction time was gone. So it collided with the pedestrian, and pedestrian died at the spot. This incident was happened in the Uber self-driving car. The argument from this incident was that system detected the pedestrian nearly 6 seconds before impact, but it never classified her as a pedestrian because she was crossing at a location without crosswalk. So there was no zebra crossing, as you can see from the image. And the system considered that the jaywalking pedestrian is not included, so it ran over, and that's why it collided with the pedestrian, and pedestrian lost the life. The another incident from this is, let's say this video, it's from Ariane 5 maiden flight from the European Space Agency. So it is takeoff now, and now it's behaving vulnerable and gone. So it exploded in the environment. Now what happened here, you can see on a right side of your screen, there is a one line of code which highlighted. The programmer used the same software from the Ariane 4 to Ariane 5, and the integer value outflow in the programming, and then it caused the error that after 37 seconds of engine start, it exploded in the environment, and total financial loss of 850 million euros. The point is, who ensures that system development is perfectly done? The answer is nobody, because it is difficult to develop large complex software and guarantee that hardware and software works perfectly when it comes into the environment integration or interactions. A problem occurs maybe cause catastrophic effect in technical application domain. And that's why we have to focus on the safety engineering autonomous vehicle. Especially today in this webinar, I'll focus only on safety, how you can find out the safety parameters, what needs to be done to make our autonomous vehicle safe. And to start that, I want to show you very funny but really interesting video. So you can see there are many cars ongoing. The audio is not available, unfortunately, but you can see the funny interaction between pedestrian, motorcycle, buses, or some transporter car, and some series of cars ongoing parallelly. No one is hurt at the end, and everyone is interacting in a way that everyone get their opportunity to just pass on it. So what I mean here is everything works fine, but as a safety engineer, we have to ask questions. What happens if this pedestrian stops at the zebra crossing? The behind transporter can stop it or can just run over him? Or what happens if this transporter just steered left or steered right? What will happen? So those questions we have to ask. Yeah, and definitely in this video, no one got hurt, nothing happened. But somehow this scenario we have to consider into account, and that's why the safety for autonomous vehicle is really necessary. So what is autonomous system basically? So the term has been used for a long time in the robotics and artificial intelligence research community, but it has some kind of driving automation systems which indeed be autonomous if they perform all of their functions independently and self-sufficiently. But it depends also on how they interact with the outside environment as well. So the role of the sensing system is to gather data from the environment, and the role of the action system is to maneuver the mechanical parts and actuators to provide the controller logic defined actions. But my point is here that autonomous system is integrated with this human machine interface. So either you can monitor your system by monitoring the sensor data and filter it out, and otherwise you put your logic that now you have to turn left or right, or you go ahead, something like that. So the HMI allows interaction with the system, controller logic which controls the system and takes necessary safety critical decision by using the data. What happened in autonomous system, everything was done by the system. So you have to, the system will also monitor, as well as system also put a logic into account, and then it behaves autonomously without any human interactions. So the autonomous system consists of sensing system, human machine interface, and action system. But the problem occurs when therefore when there is a task differentiate. So what kind of task do I have to monitor, and what kind of logic do I have to implement? So there comes the level of autonomy. So some part of the driving task, do I have to monitor the vehicle, or some part of the driving task, do I have to just leave it on the system? So the level of autonomy is defined by the responsibility of the autonomous task to certain limits between the system and the user. It also involves the duty of collecting necessary data. So you watch that there is no pedestrian, the vehicle can drive ahead, and suddenly vehicle stops, you can also take over it. So likewise, you can also some collecting measures, as well as you monitor the environment and perform the necessary actions. So the level of autonomy consists with two kind of situations. First is the different safety critical situation functions. In autonomous in vehicles, we have mainly three operations: either you accelerate, braking, or steering, right? And those safety critical control functions you can work without driver, which is you can leave it on system, or you have other safety warnings, which we can say park assist, too close to the front, or some kind of attention to the driver. So there are two kinds of level of autonomy. Once it takes the action into account, and one it provides you an alert message to the driver that now you are in a safety critical situation, you have to take over from me. And also the level of autonomy have been classified by two different organizations. As you can see from the left side, it's SAE level, which is a Society of Automotive Engineers, and the right side, it is NHTSA level, which is a National Highway Authority, National Highway Traffic Safety Administration. So, but the more or less all both organizations have classified clearly, except 4 and 5 level. NHTSA defines the level of autonomy from a vehicle that does not have any of their control from 0 to the fully automated system to the level 4. But for high automation at level 4 in SAE, the execution and monitoring and also performance fallback, which is called, like, if there is a failure, you have to have any backup plan for the system, which happens in system in level 4. How it differs from level 4 to level 5 is level 4 is only for an operational design domain. So it has you can only use level 4 in certain operation environment, which you can use it on highways, or you can use it on pre-designed environment. But level 5, you can put this vehicle anywhere on the road, and it behaves the which we designed. So all system fallbacks and performance monitor can be done in this level. So this level of autonomy also differs with the safety and technical safety. How it differs? So let's say there are the definition of safety is like freedom from those conditions that can cause death, injury, occupational illness, or any kind of damage to the environment. Well, I will go with the absence of unacceptable risk, which is very small. However, you can see absence of unacceptable risk is very generalized. I mean, for some risk, for me, it's unacceptable, and for you, it's different. So we have to consider a standard then. There comes the standard where everyone agrees that this is an unacceptable risk. But as system and technical system, the safety and technical safety also differs. So in technical safety, measure for the ability of a failure affected item to endanger neither person, property, nor the environment. So the technical safety means your system cannot endanger any person, any property, or any kind of environment. It includes everything. So it has to behave in a way that it has to provide certain safety to the user as well as to the environment, right? But before that, I have to put some of definition in here so that more you can understand what I'm going to present here. So accident, everybody knows that if there is a collision between two cars, we call it an accident. Hazard means some electric shock, a chemical reaction, or you fall down on a wet floor, walking up a ladder, which we call it hazard. The risk here is a possibility or chance of loss. So on a wet floor, you fall down and you might have a bone injury or something like that. So it's an injury, or you have a chemical reaction, you just died. So it's a loss of life, right? Well, uh, I will go with the acceptable risk because it's a level of risk that authorities or other bodies have defined. Why do I have to go with this? Because it precisely mentions that a jet engine has a historical failure rate of 0.4 million departures. Means a 0.4 million departures one times a jet engine fails. It has a value of 0.4 million departures, which is very convincing and which can be argued. But how we can find out this failure rate? Some of you know that there are some parameters that my self-driving cars 1,000 kilometers and it has no failure rate, and some of you also argue that I put millions of kilometers on these self-driving cars and there nothing will happen. So the argument is the jet engine is working on a same environment domain. If you fly from the India or New Delhi or from Europe, the environment around the jet engine is same. But when it comes to autonomous vehicle, if you consider your failure rate is 0.4 million in Europe, it won't be same in the India or it won't be same in other part of the world. So that we have to find out that parameter for each country. And to do that, we have to find out with the risk acceptance matter that how the frequency of the occurrence event on a particular harm and what is the severity of harm. So you can see the severity will go from negligible to catastrophic, and your frequency will grow from imperable to frequent. And then you define that this is my marginal risk. I will not go beyond it, but this is my acceptance. And you found out that this is my risk. So you have to minimize your risk in a way that it will come below this green line. To do that, we have three kinds of matter: MEM, which is called minimal endogenous mortality, GAMAP, and as low as responsibly practicable. The frequency edge can be quantified by probability or rates, methods for finding or modeling harmful events. Due to the potential variety in possible harms, the severity of harm can be quantified only on a very subjective basis. So some arguments you can say this is more severe, for me it's not, and likewise. So here also comes the standard into picture. Therefore, comparison of a given risk caused by a particular system with acceptable risk values are very subjective. The aim of risk acceptance is to bring about a decision in a systematic and founded fashion whether the risk under consideration can be accepted or not. In later case, the system causing the risk cannot be put operational. So if you above the red line, it cannot be put in operational. You can only put in operational when it belows the green line. So this is how you can define the risk acceptance for your particular system. For safety critical systems, that might be defined with different parameters. So the degree of benefit, like great distance in aviation. So two planes cannot be collide in the air because there is a huge distance in between, but car can be collide because there is no kind of that kind of possibility. Who is at risk? So you can say the sick person is at risk, astronauts on a outside of the space stations, travelers, something like that. And degree of self-determination. So driving a car versus taking an elevator. So how much risk is there? How many people are at risk, or compared to car versus a nuclear plant? So you also have to find out how many people are at risk. And then last is severity. So is it an injury, some kind of, or is it a person completely lost, or death or injury? So these are the parameters that influence the risk acceptance, and we have to take it into consideration when it comes to autonomous vehicle. And for that, we have to find out what kind of failure, fault, and error there in the system. So let's say failure is the inconsistent behavior with respect to specified time behavior while running a system. So each failure is a timestamp. It's like you have an airbag system, and before 10 seconds, when you collide with the other vehicle, it has to flow, and it has to save the passenger inside the car, but it didn't detect the collision, and airbag system fails. So it's called failure. What is fault inside it? So the programmer who programmed the microprocessor, he put, instead of 10 milliseconds, he put 20 milliseconds. So the requirement was 10 after collision, the 10 millisecond time for the airbag to blow, but somehow this programmer put 20 milliseconds, so it blow after 10 milliseconds, and at the same time the passenger collide his or her head with the steering, so we cannot save the passenger. The error was because of this fault. We misunderstand the statement, and we introduce a bug into the programming language, and therefore it causes error into the microprocessor. Microprocessor didn't react because it has a 20 millisecond reaction time, and that's how fault occurs. Error occurs. Error causes the failure, which leads to an hazard. So this how it flows from the fault injected by the programmer to the failure into the system. Now, what is fault tolerance here in this system? So you can leverage those system failure to occurring faults under operational condition and enable the driver to get a safe stop. So let's say you have a failure in throttle pedal control. So, and then you don't know how to accelerate. So suddenly you know that throttle pedal position won't work. So acceleration pedal. And there comes the fault tolerance system, which has a backup plan, which we can say redundant system. It activated the redundant system and safely maneuvered to the driver to the side of the roadway. What is fault detection here? So it detects and it alarms the driver that there is a failure in the throttle pedal position. So it discovers the fault in a hardware or software by trigger alarms for a manual intervention or initiate automatic recovery. What is fault prevention is to prevent such an error or bug into the program code. So we have to establish the mechanism that prevent faulty inputs or condition from occurring those fault into the program. Now, to do that, we have to build a system from the scratch, and for that we follow the V model. The V model consists from requirements, which will leads to the system design, and the system designer then sends the concept to the architecture designer. The architecture designer will build architecture and then define certain modules. So let's say we have a car, autonomous vehicle. The autonomous car designer, system designer develops certain systems, and the architecture design develops architecture, and modular designer define that this is the engine module, this is a transmission module, this is an electric module, and so on. And after that bifurcation of this module, the coding happens here at the center part of the V model. Then we will perform unit tests for each module. We check how the program behaves, which we can call it static testing. Static testing is just a verification stage to see how the code being examined without executed. So here in verification process, code will not execute. The code will execute at the dynamic testing to check whether the system fulfills its requirements or not. So these requirements, it's very necessary when it comes to safety engineering, because it defines how much safe system you want. If you didn't put here safety requirements, the engineer won't know how much safe you want, and the design went outside of the scope, and somehow you got different result at the acceptance test, which you don't want. So to do that, we have to look for this requirement section, and for that I will took small example to understand very briefly about it. Let's take a ACC functionality, which is an adaptive cruise control in the autonomous vehicle. We have one car which drives at 80 km/h at the distance of let's say 120 meters, and then there is a leading vehicle. So what ACC does is you have to set a speed, which is 80 km/h, and you have to set a safe distance. So you have to the vehicle has to maintain this safe distance to the leading vehicle, right? But in what ACC also does, it is perform acceleration and braking operations simultaneously. So when leading vehicle comes slow down, so from 100 to 50, your distance will minimize, right? And then the ACC system will maintain the safe distance set by driver and follow the same speed which is followed by leading vehicle. Once this leading vehicle again accelerate, let's say from 50 to 100, again it has a huge distance in front of the following vehicle. It is again accelerate from 60 to 80. Okay. So why we need ACC? So ACC is like you're doing acceleration and braking operation during your driving. ACC will take over those operations and make a consistent driving. In mechanical, we can see the constant acceleration or velocity can save fuel consumption. So that's why ACC is used. I built on this functionality a small architecture. Let's say this is a set speed set by the driver and set distance also set by the driver and the ACC logic controller. This logic controller has three kinds of unit. One is engine control unit, braking control unit, and distance control unit. This engine control unit also has three components. Let's say total pedal position sensor, engine speed sensor, and engine fuel pressure sensor. Okay. For the sake of simplicity, we exclude other components like this. We only included the orange one, which is a safety critical components. Okay. To do that refinement of the safety requirements, we have to perform first hazard analysis and risk assessment. Why we need to do that? Because it defines our safety goals, how much safe the system we want. And from safety goals, we know the functional safety requirements for that particular ACC system. And in that ACC system, we also need to find out what are the technical safety requirements for hardware as well as for software. So let's start with the hazard analysis and safety requirement. But the process is also explained in ISO 26262. So the determination of safety goals as part of the hazard analysis and risk assessment is also in a concept phase as well as in a development phase. So to do that, I put small example here. Let's say we have a wheel speed sensor. It has an omission. Okay. Omission is like you have an absence of signal, so you don't know what is your wheel speed sensor when your vehicle speed is greater than 50 km/h or your safe distance, which is less than 10 meters. What is the hazardous situation here? It's you have front end collision, right? And the severity is when you have front end collision, you have a heavy injury. You might call it life loss, or maybe you have a head injury because of the front end collision. The exposure level is you always required wheel speed sensor because to braking operation, you need to know how much wheel speed are, and then based on that, you have to put brake pressure lower into the or fluid pressure into the valve and compressor. The controllability is because there is a very less distance in front of you, the controllability is very low, so we put it as a 3. And based on this 2, 4, and 3, we have a ASIL level. So ASIL level is automotive safety integration level, which define a different safety critical scenario, different safety integrity levels. According to ISO 6262, which is a standard, the associated risk to the electronic and electric system needs to be identified. So as we can see, wheel speed sensor is part of the electronic system. The potential risk before the design phase. So we are designing the system. Now, during that design phase, we have to find out that what happens if our wheel speed sensor has an omission. So for this, the hazard and risk assessment method is used. And it also includes the influencing factors. As you can see, I put engine speed sensor in a delay. Then I put unintentional acceleration. So we don't want acceleration, but somehow the system accelerate and decelerate. So those things we have to take into account to find out the functional safety requirements for the vehicle system. So based on the hazard and operability analysis, there are 4 kinds of deviations. Deviations is here. So omission is absence of signal. There is a commission. which is an unaccepted emission of a signal. The wrong value, which is more or less, you don't know whether your value from the sensor is correct or not. So it also I call it omission. And there is a delay. So the timing delay in a signal. So these are the guide words we use for hazard analysis and risk assessment. There is also one method called failure mode and effect analysis, which is for safety assessment, which is very necessary. Okay. But the question is how you can find out this D value. It's a risk matrix. So the ASIL determination matrix we have different severity, as I already show you in risk acceptance matter. So severity from negligible to the high risk to the life, and from exposure very low to the high, and controllability from simple to the severe. So we don't have time at C3, but we can cover our severity from C1. And from this table, we can find out ASIL level from QM to the direction of this. Okay. Yeah. So to do that, the result of this evaluation can be classified based on the ASIL level, which is in QM, ASIL A, B, C, and D. The severity is what is the severity in the event, as I already explained to you. Exposure, how often do we have to drive in these situations? Like the wheel speed sensor has always should be there because it requires for the braking operation. Controllability, how well the driver or system can control the hazard in the event of failure, or how it can be avoided. So it's a measure which we can avoid to severity. Okay. So let's take a small example for the functional safety requirements calculations, or to find out the functional safety requirement for ACC. Let's say we have a safety requirement of ACC, which is called avoid unintended acceleration, which leads to a hazard, okay, which is an highest ASIL C level. Okay, to do that, we have two different safety requirements. One is for driver assistance systems, which is a DAS, and one is for engine control level. So to avoid unintended acceleration, the functional safety requirement for driver assist system is avoid unintended ACC acceleration request beyond the range. So you have a range from 1 to 1.5, and if this acceleration range beyond that range, you have to stop your functionalities, right? On a safety requirement side for engine control is keep acceleration request within the range. Then you more bifurcate your functional safety requirement into the technical safety requirement. And then you say fault within the ACC system detected, and ACC system has to deactivate it. So the fault you detected in the ACC system, and now you have to, your DAS, which is driving assistance system, you have to deactivate ACC system because of your failure in the system. On a technical safety of engine control side, you have to keep throttle position request because you cannot decelerate. If you decelerate, you have a rear end collision. And if you can accelerate, you have front end collision. So the technical safety requirement is keep throttle position request within the specified limits. Okay, then you more bifurcate your technical safety requirement into software and hardware. So I took a small example from the software side that due to fault in the speed controller manipulated differently, and then AC system is deactivated. Now on a hardware side, due to fault in the pedal sensor, which we used for acceleration, AC system requested terminator. So this is how you can refine your safety goals from the safety goals to the function safety requirement to the technical safety requirement to the hardware and software safety requirements. The functional safety requirement of the driver assistance system also holds the acceleration request that not go beyond the limits. So the engine control manage the acceleration within the requested range. So this is how you can find out from the safety goals to the hardware and software requirements. Now, how you can perform safety engineering for AC systems. So let's say you have find out hazardous situations. First, you have to find out the, you write down this hazardous situation. Let's say you have first hazard, unintentional acceleration leads to front end collision, and unintentional deceleration leads to rear end collision. So you write down those all hazards related to AC system. Then you merge those just a minute. Then you merge those hazard malfunctions with the safety goals. The safety goals is vehicle must be able to accelerate to reach a desired speed at any time. So though this safety goal belongs to hazard 5. What is hazard 5? It has says that jerky and fluctuation of acceleration or deceleration leads to unpleasant driving experience or create hazardous dangerous situation for front or rear end collision. Of course, yeah. And to define that, we also have a functional safety requirement, which also calculated from the safety goal. So let's say our first functional safety requirement, which is a detection of the object, must not go beyond their specified range. And it belongs to safety goal 6. What is safety goal 6? Vehicle has to maintain safe distance to the leading vehicle. And it also associated with the hazard 5 and 6, which says that object detection error can be hazardous for the jerky ride or can be hazardous for the user. So this is how you can refine your safety requirements from the hazardous goals to the safety hazardous situation, from the safety goals to the functional safety requirement. To identify more refined into the safety requirements of the system, ACC system to the overall vehicle was also used to determine the safety goals. So after performing intensive HARA method on the ACC system, following malfunctions, which show you HZ 1 to 6 in the ACC system can be defined as a potential hazard. The determined potential hazard is further to the development of the safety system goals. And then in order to classify the system duty for developing the safety concept, we also find out the functional safety requirement of the system, which defined based on the safety goals at every level of abstraction of the vehicle system. So this is how you can do your safety engineering for particular AC system functionalities. To simplify this in 4 steps, I would say there are identification of general behaviors, situations and related accidents. So you wrote down it and then you put it into the database. You also identify the malfunctions by detecting of those deviations, which I discussed with you, that omission, commission, delay, or wrong value. Then you formalize your malfunction, that at what speed and how much distance do I have for this malfunction, so is very hazardous. And then you include as integrity level determination, which is ASI level, automotive safety integrity level determination. You in design phase you include all the parameters, but when it comes refinement process, you remove those parameters whose integrity level is too low. So let's say QM or A should not be included when it comes to safety engineering. And then you identify the cause for those deviations and to find out a concept for safeguarding against any kind of deviation in that particular concept. And to do that, I put some of the ideas on it. Let's see. I put this ACC on Curve Road. So there are 2 vehicles. One is leading vehicle and one is following vehicle. The following vehicle only starts when there is a distance defined by the user is satisfied. Once this distance is satisfied, the vehicle drives, and it also brakes when the leading vehicle stops. So you can see here throttle and steering and braking happen. So now throttling happened because there is a distance. Now is braking happen because the leading vehicle stops. So this is how you can simplify your functionalities, as well as you can also check the safety concept. You can see from the right side of the screen that vehicle from the leading is outside the lane and creating unnecessary reaction for the ACC logic, which the following vehicle on a left side is immediately responds and brake the vehicle before it collide with the leading vehicle. So this is how you can put safety engineering into autonomous vehicle and see the reaction, how it behaves in a virtual environment. I also put some weather change during driving. So let's say weather impacted on different sensors, some kind of visibility loss, the camera sensor won't work. So at that time, we can have to use LiDAR or radar sensors. As you can see from my this virtual environment that I use, it's I don't know, it's showing a rainy, but somehow it's not visible for you, but it's raining happen and it's still working. My ACC model is completely fine with it, and it stops before it collide with the leading vehicle. Some of the implementation I also did it with MATLAB environment. So these examples are already implemented in the MATLAB environment. So let's say you have an ego car, you have a leading car, and you have a sense data, and then you simply simulate your adaptive cruise control, which gives you different acceleration and velocity profile. As you can see, when the red one is the ego car and the blue one is the leading car. So when leading car accelerate, my ego car will also accelerate. When my leading car brakes, my ego vehicle also brakes, and it maintains a distance between two cars. You can see here and here. It won't collide with the leading vehicle in this algorithm as well. I also implemented this same concept for automated parking valet, where you can park your car without going into park place. So you just have to put indicator over there, and your vehicle just drive away. The question might be arise that why you want to park somewhere else when you have empty spaces here. The idea is I just want to show you that even if all places are full, my vehicle will go to that places where it intend to go, and it precisely maneuver the vehicle in a way that we require without harming the other elements into the surrounding environment. So, and the last one, we also implemented some of the radar sensors for this ACC system. So you can see there are three vehicles, one on the orange, one yellow on the front side, and the purple on a very far ahead, with three different kinds of visibility on radar ranges. We can see from this range angle plot. The problem is when the orange vehicle just pass on to the blue vehicle, it occurs that there is an error in the radar sensor. So if there is even if there is no vehicle on our right side, the radar still detect that there is an object. So it's a failure, and we cannot be considered as a sensor value into our algorithm. So those things we have to evaluate into this virtual environment. By showing this kind of videos, I want to show you the implementation part of the autonomous vehicle for this safety concept development. But there are still some of the open scenarios and uncertainties where we cannot work on. Like for example, in scenario 1, if you are driving behind your leading vehicle and suddenly water splashes occurs, and we know that radar sensor values deteriorated during this water splashes, it can detect as an object, and suddenly you brake your vehicle, and it can collide with the rear end collision vehicle. So, and some of also scenarios like the curve road scenario happens when your radar angle will go outside of the curve road. It can also happen. It can also be possible that hazardous situation in this kind of scenarios. Some of the bike riders outside of the radar ranges or metallic component on the road vehicle can also create chaos in this environment. So there are some open scenarios and uncertainties when it comes to autonomous vehicle, but it can be possible with different safety concept, and it can be overcome with different ideas. Now I want to discuss with you what are the challenges for Avis. So the first is the support infrastructure. We don't have that kind of infrastructure where you can put any vehicle on anywhere on the planet and then test it, because there are traffic signs differs, road marking differs, types of road surface, breeze restriction, and sometimes if you drive in the tunnel, the video camera or radar might detect as a ghost object, which is very critical for algorithm to identify. The second is environmental effects, so weather condition, or if you put camera in front of the sunlight, it just blind it, so it's also affect the performance of the Avis. There is vulnerable population, of course. The pedestrians came into the street, and it can create safety critical situation for autonomous vehicles. The localization support navigation, global navigation support system availability is very less due to the might be weather condition or not available infrastructures. Then compliance with the traffic rules, traffic regulations are different country to country, so we have to take into consideration when it comes to development of autonomous vehicles. And then there is a vehicle to infrastructure communication. The interaction with the outside infrastructure and cloud data is really important when it comes to autonomous vehicles. However, there are some also challenges on the system side. So sensor information and faulty sensors can reduce the performance at night, or in a weather condition, your radar will not perfectly detect an object in a rainy or in a snowy condition. The perception, it's a wrong perception of the object. Distortion in rain or glaring into the environment can also cause an error on a system side. Unplanned behavior, even if you don't plan for such behaviors, the vehicle predicts that behavior and behave in an unprecedented way that we cannot predict. The prediction, so again, the wrong prediction, the sudden changes and optical illusion can also cause an error on a system side. Then there is artificial intelligence. So you train your model with lots of data, and then you have an overfitting and underfitting. The things which you have to predict, you can overcome and underfit without any kind of error. So that can also leads to an error for a system side algorithm. Then there is a loss of reaction time because of the, as we can see on our first video of accident, that even if there is the sensor predicted, then there is there was a pedestrian, but it won't react in a time. So the loss of reaction time could cause a loss of life, and that's what happened. So what are the key takeaways from these webinars? Let's say first is lack of system engineering, that leads to low quality similar to software engineering, and comprehensive understanding of process models and techniques are also needed. The second is risk acceptance. So until what risk value we can accept sorry, such risk acceptance value when it comes to autonomous vehicle. There are still challenges, and the roadmap for safety engineering autonomous vehicle is far ahead. You have to think about those challenges as well. Of course, we can take support from the standard which is available. The support by standard is needed, especially when it comes to critical properties such as safety. And the question is, what are the starting points to realize such systematic engineering process for autonomous vehicles? So country like ours, it has a very dynamic population and behavior when it comes to the road vehicle safety and all. So from where to start? I think we have to start from the scratch to develop such system for the supporting of the driver, so that they can minimize the human error. You know that the statistics from the 2015 says that 80% of the road accident caused by the faults of driver or passenger. If we can minimize 50%, we can reduce 50% of the road accidents. So we have to provide such systems to the drivers, so that they maybe collision avoidance system or emergency brake assistance system can standardize into the car, so that it cannot collide with other vehicles, and loss of life can be saved in our country. So far, some remarks regarding this webinar. So what are the pace of autonomous vehicle development in the world? So I think I'll show you the map, Initiative on Cities and Autonomous Vehicle. This is an US map, and sorry for the low internet. So you can see these cities have already implemented autonomous vehicle, or they are implementing right now for autonomous vehicles. We can see some of the parts of our neighboring country, but where is our country? Nowhere. So I think that we have to work on it. And last part is I told you that life in Germany after bachelor's degree. So why Germany? I think there are no tuition fees like US and any other English-speaking countries. Your public universities in 15 of its 16 states charge no tuition fees to students. So the international campaign was commissioned by the German Federal Ministry of Education and Research, and the idea is to increase the number of highly qualified foreign students to a German university. That's why there is no tuition fee regardless of the nationality. The history of innovation and ingenuity, you all knows about the German technologies as well. A proudly international outlook. There are students from the South America, Europes, and other parts of the world. So you also have an international outlook. Affordability is very convenient for our students, Indian students especially. Compared to any other English-speaking countries, there are 120 credit points master course, 90 from the subjects and 30 from the dissertation. You can also check out. There are 400 universities in Germany and more than 20,000 degree programs. So that's quite a lot of choice. So you can look into that also. In my university where I'm working right now, that TU Kaiserslautern has different kinds of master courses available in English. I studied this interdisciplinary program, commercial vehicle technology. You can also look for biology, computer science, and other interested program course. And if you want more information, you can also log into this website. There are many agencies they are working on right now with this education in Germany, but yeah, you can contact any of these, or you can you can get information on this website as well. So yeah, thank you for your attention, and get in touch with me for your further details. If there is any questions, I will open to you.
So thank you, Anil sir, for the wonderful session in the autonomous vehicle. Now I would like to request Ms. Renuka Patel ma'am for the question answer session. Over to you,
Yes, sir.
Renuka ma'am.
Yes, sir. So it was wonderful session. All the
Mhm.
inquisitive viewers have specially focused on questioning the challenges faced in automotive industry. The first question, one of the viewers said, can you describe the role of safety engineering in automotive part?
So that's what the role of safety engineer for automotive part is to provide a safety assistance to the driver. So as you can see from the plot that there are more than, let's see, more than 80% lives lost due to the driver failures, right? So we can minimize those. Wait. So we can minimize those error by putting some of the technologies into the cars, which provide the support to the vehicle. So let's say the car collision avoidance system, you can put collision avoidance system into the car, which provide assistance to the driver in case of an inattentional or overspeeding or something like that. You can also put emergency braking maneuver systems into the car, which also minimize the impact into your front and rear collision. So those things should be standardized and should be put into the car. It's already there in this country. They put from last 10 years, they standardize the process. So in every car in Germany, if you buy it today, those functionalities should be there. That's how they are managing the crash scenarios on road vehicles.
Okay, and same thing, it includes safety features in e-vehicle. Like you
Sorry?
said, it will prevent the crash, no? To prevent some kind of crash or crash with an obstacle. Safety
Yeah.
features or thing we have to take care. So what are the other safety features in e-vehicle?
So there are safety features for, let's say, in my example, let's say adaptive cruise control, we have an unintended acceleration. So you don't want an acceleration, but somehow the system detect and accelerate itself. So you have to stop this unintended acceleration first of all. For that, you have to additional features which put into the system, which says, no, you don't have to accelerate because there is not enough space in front of you. So you built an algorithm in a way that minimize those kind of error or failure in the system. Now, coming to your question, you say the safety features. The safety features is divided into the active and passive. The active safety measures are like the tensioning of your seat belt, or let's say the airbags from the side and from the front, or something like that, which prevent the passenger to die or something like that. But on a passive side, you don't have anti-lock braking system. You don't have ESP, which is the stability program, and all those functionalities should be there. It's not included in a vehicle in a way that it should be there. Somehow the problem occurs when the functionality stops working, or it's manipulated with some kind of errors. So that's we have to look into account.
Okay, and one more question. Is there any need of special lanes for autonomous vehicle on expressway?
I think there is no need for any special lanes for autonomous vehicle, because it also has a lane keeping assistance system. So if you are driving on a right lane, your vehicle will just drive on a right lane without any maneuvers. But if the front vehicle brakes, it has to maneuver on a left lane. So some kind of functionality is already there, which is called lane keeping assistance system. We don't need special lanes for autonomous vehicle. However, we can guard such systems like PRTS or something like that on autonomous vehicle. The reason is, or why do we need autonomous vehicle is, it can minimize your fatigue. So you have to travel from Surat to Mumbai, takes 6 hours. You just put your autonomous vehicle, switch on it, and then read your magazine or newspaper, whatever you want. So it minimizes your fatigue. It also minimizes your error, because sometimes you're tired and you misinterpret the situation and you collide with other vehicles and you endanger other person as well. So you are not endangering you as well, but you are endangering with the other person, who have no idea about you, because you are traveling from the Surat and the person just came from the Valsad or somewhere else. Yeah. So don't need for any additional lanes. However, we can focus on it, and we start implementing some small functionalities into the car, so that we can minimize this fault of the driver or fault of the passenger. And maybe as Chirag sir commented, there are around 4 lakh people per year died due to road accident. So we can also minimize, even if we can minimize 50% of this fault of the driver or passenger, we can minimize this 50% death. So we are saving 2 lakhs per year. So that's a huge number, madam.
Okay, sir, got it.
Yeah.
One more question. What is TCS system in vehicle, automotive vehicle? Traction control system.
Yeah, so traction control system manages the vehicle to put a torque input on equal side of the wheel. So you are steering on a curve side with a high vehicle velocity. As a physics, your vehicle backside would go outside the road, right? But traction control system manages those torque into the wheel, that it will not go outside the lane, and it will maintain the curve precisely to maneuver the vehicle.
Okay, and sir, regarding it, okay, one more question. What about the physically obscured or disabled sensors? Like you have explained that you have an environment challenge, like the tree branches, insects, like bee swarms or locusts. So how it is managed? How sensors are useful?
So there comes the sensor fusion part. I think it's a nice question that Vishal has asked. So the sensor fusion comes with you have a radar sensor, you have LiDAR sensor, you have vision sensor, so like camera, high definition camera on all part of your front side of your car. And if your one sensor won't function correctly, you can rely on another one, and you can, as well as small radar sensor fail, you can also rely on LiDAR and something like that. So there you have a barrier of safety. So if one one radar fails, you have a LiDAR and camera sensors. When your LiDAR and radar both fail, you still have a camera, and all sensor fails, the functionality has to stop. So you cannot drive more autonomous mode because all sensor modes are completely failed.
Okay, and one more question by my colleague, Professor Sushant Merai. He wants to know what is the effect of RD on autonomous vehicles?
What is RD?
I think it's rare division emission.
I'm not aware about it, RD, sorry.
Okay, no issues. And one more question from my side. Like you said, there is a challenge regarding AI. So how a path is defined and represented in automotive industry?
So the machine learning part you are talking about, right?
Yes, exactly.
So as I told you that in machine learning, when you train your model with lots of kind of data, like thousands or millions of data, sometimes you are train your model either in an overfitting way or an underfitting way. You don't know the precise fit model because the situation is out of control. So you manage to have the data which is very supportive for training your model. So let's say you have put all kinds of scenarios, but when you put in said scenario, there are many types of scenarios. You are putting already overloaded information into that. So those things we have to avoid it. You have to so what I'm doing right now, I'm also working with the machine learning. So what I do is I choose the safety critical features. So let's say in my SCC model, I'll choose only acceleration, braking, and steering part. So those three are critical, and inside these three I will only look for throttle pedal, braking pedal, and steering position. Okay, so you minimize in a way, you choose these three safety critical features, and now based on these three sensors, you put a data algorithm and check whether it is feasible. First, you have to check feasible. If it's feasible, then you optimize the frequency, optimize the efficiency. If it's 60%, you will load more data and it comes to 75%. Then you load more data and it comes to 95% or 96%, something like that. But if you put every sensor on the car into the model will go outside and it won't react away what you might be predicted.
Okay. Just last question from my side. Like, can we see this as this automotive vehicle collaborating with e-industries or
Collaborating
electric
what?
vehicles, e-vehicles, electric
Yeah, I
vehicles,
mean,
and autonomous?
you just
Totally.
have to replace internal combustion engine with electric motor. So there is
Oh,
no option at all. The
okay.
autonomous vehicle is like you don't need a driver to attend
Yeah.
the road and surrounding environment. So that's a clear definition of autonomous vehicle. So either you put traction motor inside auto, or either you just replace IC with any kind of traction motor with fuel cell or any energy source. That's not an issue at all.
Correct.
Yeah.
Okay, sir. So that's it for today.
Thank
Today's
you.
question.
Thank you.
I
Thanks
hand
for
over
wonderful
to
questions.
CRD sir, Chirag Desai sir.
Okay.
Thank you, Anil sir, for the informative presentation on the automotive vehicle. I think our students as well as faculty also gain many things from your webinar. So thank you very much. Now I would like to conclude this webinar by vote of thanks. So I would like to thank Anil sir for providing this opportunity and sparing his valuable time for this webinar. I would like to extend my sincere gratitude to our principal sir, Dr. Latesh B. Chaudhary sir, and our head of the department, Dr. K.B. Rathod sir. I also would like to thank my colleague, Professor Sapan and Sanuka Patel, for sparing valuable time for the webinar. And at the last, I would like to thank our management for providing such a beautiful platform to arranging this webinar. So thank you, Anil sir, for sparing your
I,
valuable time and
yeah.
doing for our students. Thank you.
I also like to thank
I
all of
think
you, Chirag sir, Joshi sir, madam, and the management staff from the RNGPIT, also the Rathod sir, head of department, for giving me an opportunity to share some of my work with you all. And thanks a lot again.
excellent presentation, sir. I think I should end this broadcast. Thank you.
Thank you.
Thank you, sir.
Bye bye, guys.